Welcome back again to Physics Galaxy, and today we're going to solve some quantum mechanics problems which were asked in last year's CSIR NET examination, and that this is part second of the last tutorial. Okay, so the first problem is the Hamiltonian of the one-dimensional quantum harmonic oscillator is given by like this. So h equals to p square by 2m plus half m omega square x square. The expectation value of d comma h in the ground state y d equals to 1 by 2 h cross xp plus px is okay in units of h cut omega. So we need to find the expectation value of this commutator d comma h, okay, it's the expectation value. So what we need, so we know d, we know h also, so let's see. So what we have, okay, so let me drop, I will find the expectation at the end, but let's solve this commutation relation first. D comma h, okay, so d comma h will be equals to d comma h, we know it's p square by 2m, p square by 2m plus half m omega square x square. Okay, so we can use the identity of these commutators, so we can write like this: d comma p square by 2m plus d comma 1 by 2 m omega square x square. Now the commutators don't act on, if we have constants we can take them out, so we can write 1 by 2 m d comma p square plus m omega square by 2, which is a constant, so d comma x square, right? So what we need to find is these two commutations, d comma p square and d comma x square. Okay, then we had to find the expectation value. So let's first find d comma p square. So d comma p square we can easily find using the relation. So we know from quantum mechanics that if we have, suppose, some function of x comma p, so we know already that it can be given as iota h cut dou f by dou x. Okay, so this we already know, but we don't have d comma p, we have d comma p square here. So we can write d comma p square equals to p, again using the identity, d comma p plus d comma p, then p outside. So this is again the other identity that we have used here. Okay, so let's see. So then that we can find d comma p here, so we can write d comma p equals to iota h cut using the identity here, dou by dou x of d, right? So which is equals to iota h cut dou by dou x of, and what is d? D equals to, so d is equals to 1 by 2 h cut, so that 1 by 2 h cut, we have xp plus px, so we can write iota by 2, then p plus p, so that is equals to, so that's equals to simply iota p, right? So this is dp, commutation of d with p, so it's iota p. Okay, so then what we will have, d comma p square will be equals to p, so it will be equals to p, so we have p here, then d comma p, that is iota p, then we'll have d comma p, which is again ip times p, so it will, on the whole it will be equals to 2 iota p square. Okay, similarly if you find this commutation relation, so it will come out to be minus 2 iota x square. Okay, so what, now we have both these commutations, 2 iota p square minus 2 iota x square. So then we can find the total commutation, so d comma, so we can find the total commutation, that is equals to d comma h, that will be equals to 1 by 2m 1 by 2m 2 iota p square plus m omega square by 2. So we shouldn't write the commutation then. Okay, 2 iota p square plus m omega square by 2 minus 2 iota x square. Okay, so 2 gets cancelled out, 2 gets cancelled out, so we can take iota common, so p square by m minus m omega square x square. Okay, and now we can okay, we can put 2 here, so 2 here, then we have to multiply 2 here. Okay, so this is the commutation relation d comma h, but we have to find the expectation value of this. So the expectation value of this is what we need to find out. Okay, so that means expectation value of this, right? So we can write it's equals to 2 iota, so we can write it expectation value of, so this is nothing but the kinetic energy, right? Expectation value of kinetic energy minus this is nothing but potential energy, right? So expectation value of potential energy. Now we know that the total energy in case of harmonic oscillator equals to, so that is equals to the ground state, because the question asks in the ground state. Okay, so ground state, so we know in the ground state total energy equals to half h cut omega, and that is equals to the expectation value of the kinetic energy plus the expectation value of potential energy. So that means the expectation value of kinetic energy equals to half of the total energy, so that will be equals to one one fourth of h cut omega. Similarly, the expectation value of the potential energy will also be one fourth of the total energy. So this is equals to one fourth of h cut omega. This equals to one fourth of h cut omega. So that means the expectation value of d comma h equals to 0. So the option is 0. Next question is again from the simple harmonic potential, and denotes the eigenvector of the number operator for a particle of mass m in a one-dimensional potential v equals to 1 half m omega square x square, n equals to 1 comma 2 and so on. For the state vector phi, which is given by like this, we need to find expectation value of x. Okay, so phi is given, but this is phi at t equals to 0. So at any time t, phi will be given as, if I am assuming that this state is having energy E1 and this energy state is having energy E2, then my state function at any arbitrary time will be equals to 1 by root 3 e to power minus iota E1 t by h cut 1 plus 1 root 2 by 3 e to power minus iota E2 t by h cut 2. Okay, and I just need to find the expectation value of x. So expectation value of x at any time t is given by, if we use bracket notation, bra phi x operator, then get phi. Okay, so we can solve this. Okay, so first we'll write this one. So it will be simply nothing e to power, there is minus iota, we have to write iota e1 t by h cut root 3 then 1. Okay, plus root 2 by 3 e to the power iota e2 t by h cut 2. Okay, then x operator, and then ket. So ket is simply this one, so it will be equals to 1 by root 3 e to the power minus iota e1 t by h cut 1 plus root 2 by 3 e to the power minus iota e2 t by h cut 2. Okay, so we need to solve this expectation. Okay, and that's it. So one thing to remember is So because some diagonal elements will cancel out, because this, when we'll operate with this one, will get 0. Why? Because this is an odd function. Okay, as we know, for a simple harmonic potential, so if we have simple harmonic potential, well, so like this, we have even odd functions. So first function is an even function, the second function is an odd function, and so on and so forth. Okay, so I have even, odd, even, odd. Okay, okay, so that will make 1 and 2. Okay, so this will cancel out with this. Similarly, 2 will cancel out with 2. The only remaining terms will be the diagonal terms. Okay, so the diagonal terms remaining will be 1 with 2. So e to power, okay, we had to also take care of the constants. So we'll have root 2 by 3 e to power iota e1 t by h cut, and then e to power minus iota e2 t by h cut, then 1 x operator 2. Okay, and then we'll have one more term, that is root 2 by 3 e to power iota e2 t by h cut, e to power minus iota e1 t by h cut, and then we'll have 2 x operator acting on 1. Okay, so these are the only two terms remaining. Okay, so so this means we can um okay, we can write root 2 by 3, we can take common. Okay, and then we'll have, so root 2 by 3 here, root 2 by 3 here, so we can take also. So we can write like this. So iota e1 minus e2 t by h cut. Okay, then we have 1 x2 plus e to the power minus iota e1 minus e2 t by h cut, then 1, so the 2 x1. Right? Okay, now this and we already know 1 x2, its conjugate will be 2x1. Okay, and this e to power iota theta plus e to power minus iota theta, so we can simply use Euler's identity, so it will be equals to twice cos, right? So twice cos of e1 minus e2 by h cut t, then we'll have 1x2. Okay, okay, there is 3 also, right? Root 2 is also there. Okay, so this is our expectation value of x. So what we need to find is, what is this 1 of x2. Okay, so we already know that this x is an operator, and it's equals to h cut by 2 m omega, and then we have the raising operator minus or plus the lowering operator, right? So what we can do, okay, so we already know this, so we'll have h cut by 2 m omega, and then we'll have 1, then we'll have a plus a minus acting on 2, right? Now this, when a plus will act on 2, will have 3, but then it will be orthogonal to 1, so that will give us 0. But when a minus acts on 2, so when a minus acts on 2, we'll have root 2 1, so that when multiplied by this, so we'll have 1. Okay, so basically what we'll have, so instead of this vector, we can simply write root h cut by 2 root under root of h cut by 2 m omega, then we'll have root 2. So, okay, so the final answer will be expectation value of x will be equals to, so it will come 4, so root 2 here, that will equals to 2. and 2 into 2 4, 4 by 3, and then we'll have under root of h cut by 2m omega and cos of e1 minus e2 by h cut t. So this is our final answer. So let's see in the options. But there is cos of omega t. Okay, so I can assume that e1 minus e2 by h cut equals to omega. So then the option is this one. Third question is, the ground state wave function for the hydrogen atom is psi naught equals to 1 by, okay, so root 1 by pi a naught cube e to power minus r by a naught, where a naught is the Bohr radius. Okay, considering an additional potential h dash as a perturbation to the hydrogen atom Hamiltonian given by. So this is our perturbation. Okay, and perturbation is applied only from 0 to r, capital R. When r greater than capital R, there is no perturbation. Okay, when r is the radius of the proton, r is very less than a naught. Okay, so a naught is the Bohr radius. Okay, the shift in the ground state energy due to h dash. Okay, what is the shift in the energy due to this perturbation? Okay, delta E. So that we know is given by the expectation value of this h dash. So that we already know. Okay, so we can simply write. So its psi is given. So psi is given as 1 by pi a naught cube. So under root of 1 by pi a naught cube e to power minus r by a naught. So it's simple. So find the expectation value now. So it's integral 0 to r. Okay, so after the r greater than capital R, there is zero perturbation. So I had to only evaluate this integral from 0 to r. So then it will be 1 by pi a naught cube e to power minus 2r by a naught, and then I had this perturbation, that is e square by 4 pi epsilon naught 1 over r minus 1 over capital R over the volume. Okay, so that means 4 pi r square dr. So we just need to simplify this integral. Okay, so we can take this out. So 4 1 by 4 pi square a naught cube, just taking out the constants, a naught cube epsilon naught, in the numerator we have e square 4 pi r square, not r square, sorry, 4 pi, and then integral will have e to power minus 2r by a naught, and then we'll have r minus r square by capital R dr, 0 to capital R. Okay, so 4 gets cancelled out, pi gets cancelled out, so we'll have simply e square by pi a naught cube epsilon naught. Okay, so now we just need to simplify this integral, but we can use the condition that is given already, that r is very less than a naught. Okay, so then this factor will equal to 1. Okay, almost equal to 1. So we just need to simplify this integral, 0 to capital R minus r square by capital R dr. Okay, and that will become e square by pi eps a naught cube epsilon naught, then it will become r square minus r square by 3. Okay, so this is it. Okay, 2 here also, so it will become e square by pi a naught cube epsilon naught r square by 6. So this is your answer. This is the shift in the ground state energy. The last question is, the probability density of a free particle of mass m at t equal to 0 is given by this Gaussian function exponential minus x square by 2 sigma square at t equals to at t greater than 0, its probability density is proportional to this, again the Gaussian function, where sigma square at any arbitrary time is okay. So initially the particle density or the probability density of a free particle is given by the Gaussian wave function. Okay, so at late time we know how it evolves, so it always remains a Gaussian. Okay, it flattens out, okay, as time progresses. Okay, so we have to find this sigma square. Okay, so psi, let's suppose psi is proportional to e to power minus x square by 2 sigma square, because we are not concerned about the normalization constant and all those parameters. Okay, so psi is proportional to this Gaussian. Now we know psi at any time t will be proportional to integral phi, that will be the state function in the key space, multiplied by e to power iota kx minus h cut k by 2 mt dk. Okay, so this we already know, right? Where phi of k will be, so phi of k, if we know psi is given by the Gaussian, phi of k will also be a Gaussian, and it will be proportional to e to power minus, it will be equals to minus k square and then sigma square by 2. Okay, it will have same uh, functional form. Okay, now we just need to solve this integral, so it will be proportional to integral phi of k, we know it will be e to power minus sigma square k square by 2 and then e to power iota kx minus h cut k t by 2 mtk. Okay, right, so again proportional to integral e to power, okay, k square we can take, okay, so here it's k square, so we can take k square factor out, so minus sigma square by 2, then we'll have minus, no minus, plus h cut t by 2 then k square, then we'll have plus iota kx dk. Okay, okay, now this is a typical form for these kinds of problems, and we can use completing the square. So if we have suppose uh, ax square plus bx, we can complete the square and write it equal to y square minus b square by 4a, right, where y equals to under root of a and then x plus b by 2a. So this we already know from 10th class, complete the square. So that means this, so let's suppose this is our a, suppose this is our a, this is our a, and this is our b, this is our b. Okay, so that means, so it will be proportional to integral e to the power um, y square, so y square के बदले root, so okay, so whatever we have for y, so whatever we have for y, and then there we have e to power minus b square by 4a dk. So whatever we have for this, okay, we can put y, that is under root of a, then x minus b by 2a, because we're not concerned about this factor, because it will be integrated with respect to dk. So the only factor we are concerned about is this. Okay, so let's just take that one, so that will be e to the power, okay, so and this will not be integrated because in the exponent it's a constant. Okay, so e to power minus b square by 4a, so which will be proportional to, which will be equal to, okay, equal to e to the power minus, what is b square, so P is this, so that is minus iota x whole square by 4, and a is this thing. Okay, so it will be sigma square by 2 plus h cut t by 2m. Alright, so it will be equals to e to the power x square by 4 sigma square by 2 plus h cut, and there was iota also. Okay, there was iota also, right? So here we have iota. Okay, so iota यहाँ पे भी iota t by 2m. So this is uh, the final exponential that we have. Okay, now what we need, okay, we have to put it in this form, 2 sigma square. Okay, so it will be equals to e to the power x square by 2, then we have sigma square um, plus sigma square plus iota h cut t by m, right? So this sigma is actually at sigma at t equal to 0. Okay, so this sigma is actually at sigma of 0, sigma of 0. Okay, so now what we need to do, okay, so we need to square the function, because ultimately we have to find probability square. That means e to the power x square by 2 sigma square plus iota h cut t by m, then multiplied by its conjugate x square by 2 sigma square minus iota h cut t by m. Okay, so that will be suppose equal to e to the power x square by 2, then we'll have 1, okay, bases are same, powers are added, sigma square plus iota h cut t by m plus 1 by sigma square minus iota h cut t by m. Okay, so finally e to the power minus x square by 2, so this will be equals to okay, so twice sigma square by sigma 4 plus h square t square by m. So this is our form. Okay, so this will be sigma square, right? Sigma 4, right? So one, okay, so we can cancel one sigma square, so it will be e to power minus x square by 2, then we'll have 2 divided by sigma square plus h cut square t square by m sigma square. Okay, so this is sigma at any t, so sigma as a function t, so sigma naught square plus h cut square t square by m sigma square at t equal to 0, right? So if we look at the options, okay, if we look at the options, it's option number 1.